Sir, volume is very low.
Is it audible?
Audible, sir, but it's too low.
To the maximum volume. Now check it. How is the volume? Is it audible now? Is it audible for others? I have given the maximum volume. Is the voice clear? Anybody else? Unmute your mic and tell me.
No, sir, it's too low.
Sir, we can't hear you.
Now is it audible? Now?
Still it's low, sir, but comparatively better.
Shall I start? Is this voice audible or should I once again rejoin? Or is it? Are you able to hear?
Yes, sir.
Should I make any adjustment? From my side, I have done everything. I will increase the volume, that's the maximum volume. Anything else I can do here? Hello? Hello, is it clear now?
Yes, sir.
Now
Yes,
clear?
sir.
Okay, done. Why only 4 students have done the assignment? Where are the rest of the other students? Why you have not submitted the assignment? Huh? Why? It was done, all the problems was done in the class and also the PPTs were shared. You can just go through the PPTs and could have been solved it. Okay, starting the second part of the module 1. Second part of module 1. It's give me a minute. Okay. It's shear stresses and strains. Until now, what we have discussed, let us consider. I will explain this with an example. I will consider a bar which is subjected to assume this is subjected to axial loading like this. P. Now, if I take the cross section like this, okay. Due to this P, there is internal resistant force setup, and resultant of this internal resistant force I will call it as F. On the other side, there will be an equal and opposite internal force setup. Okay, that I will also internal force setup throughout the area of cross section. I will call it as F. Since this stress is perpendicular to the area of cross section, this is called as normal stress or average stress. Since we are talking about very less value of stress, this is called as the minimum stress or normal stress, are also called as average stress. Why average stress? In a sense, I am taking average of all these forces and I'm finding resultant, and then it is called as average stress. This is also called as or average stress. Average stress. Whereas when we talk about shear stress, let us consider a rivet like this. This is a plate. This is a plate, and this is one more plate. I'll indicate another color. This is one more plate. These two plates are joined, or I can say fastened. These two plates are fastened with the help of rivet, like this. There is a rivet holding these two plates, and this there is no gap here. When I apply a load tangential to this place, when I apply a load like this, the axial loading on the plates, in this junction, if I take the upper part of the rivet, there are shear stresses which are developed. I will exaggerate on this, write this. If I take the upper part of the rivet, there are shear stresses which are built parallel to the surface, and if I take the resultant of this, if I say ft, now this the resultant of the shear stress is given by this resultant force ft by a unit area of cross section, or generally you can say force per unit area. There are generally only two types of stresses. One is the normal stress, which is perpendicular to the cross section, and the shear stress, which is parallel to the cross section. You can see here all the stresses are, there is a resultant forces are parallel to the cross section. If I take the resultant force Ft, it is also parallel to the cross section. And if I write this, that resultant force per unit area of cross section is your shear stress. Similarly, on the bottom surface, I can write like this. If I take the resultant, if I write the stresses like this, and if I take the resultant Ft, the same thing holds good. You can see the difference here. This whatever, this was perpendicular to the cross section. This was a cross section, and the stresses were perpendicular to the cross section. Whereas this here, stresses are parallel to the cross section. This force per unit area of cross section, this tangential force per unit area of cross section is called as a shear stress. Its unit is also Newton per mm square, or MPa, or Newton per meter square. Okay, this is shear stress, and this type of loading is this type of configuration is called as the single shear. What is double shear? We'll discuss. Why single shear? In the sense, shear is happening at only one area of cross, at only one surface. Shear is happening at the junction between these two plates, and this is only the one area of cross section is one area is shared like this. It has been made into two pieces. Only one area has been shared. Hence the name single shear. Okay. Hope you understood this. When we talk about shear stress, when I discussed Hooke's law, we said that stress is directly proportional to strain within proportional limit. When I remove the constant of proportionality, we will get Young's modulus C. On the same lines, there is something called as shear strain. Shear strain. Shear stress is proportional to shear strain within within proportional limit called as shear stress is proportional to shear strain within proportional limit, and the constant of proportionality is called as rigidity modulus. It is indicated by G. Shear stress is proportional to shear strain indicated by gamma within proportional limit. When I remove the constant of proportionality, I will get something called as rigidity modulus, or tau is equal to G into gamma. Shear stress is proportional to shear strain within proportional limit. If I remove the constant of proportionality, I will get the constant of proportionality limit, the constant of proportionality as rigidity modulus G. So what is meant by shear strain? Let us consider a plate like this. Initially, the plate is like this. Okay. Now, let us assume that this end is fixed. I will apply a load. Shear stress in the sense the load has to be tangential to the surface. I will apply a load P like this. When I apply a load P like this, there is a change in angle. This I will call it as pi, or you can call it as gamma, whatever. You can say pi if you want. You can this is A, B, C, D, D dash, E dash. Therefore, tan pi is given by BD dash by AB, which is equal to shear strain, gamma. This ratio, this change in angle, I'll explain this. For small angles of pi, tan pi approximately equal to pi, or pi is equal to gamma. It means that the change in angle when you apply a tangential load, the change in angle, whatever the change in angle pi, is the shear strain. When you take a bar like this, and if you apply a load P like this, the increase in length, whatever the increase in length was along translational, the increase in length was the deformation. DL is equal to PL by E. It is nothing but increase in X dimension or Y dimension or Z dimension. Change in length or width or thickness is your this one deformation. Whereas if you take the ratio epsilon is equal to DL by L is your strain. Whereas shear strain is nothing but tan gamma, which is nothing but change in angle, which is nothing but BD dash by AB. Then this change in angle, initially the edges were parallel, edges were perpendicular to each other. When I apply a shear force, then the edges moves the sideways, and there's a change in angle, and this change in angle is the shear strain. Given by tan pi is equal to BD dash by AB, and this is the shear strain gamma. For small angles of pi, tan pi is approximately equal to pi, and pi is equal to gamma, where gamma is the shear strain. Have you understood this?
Yes, sir.
Right?
Sure.
Okay. Now let us talk about a problem which is also an example for double shear. So the problem is like this. Moment. This problem. Facing difficulties with this nib, this lead. Wait for a moment. It's not smooth. It has gone. I think. Give me a moment. Give me a minute. adjust for some time. I'll make it proper. Okay. Okay. Now this I should have indicated. Okay. Not able to write properly, but we will adjust this. See, what you have to understand here in this problem, what he has asked is he has given, he has said that there is a tensile pull of 80 kilonewton, 80 kilonewton. On this side also there is a tensile pull of 80 kilonewton. He has asked us to find the diameter D, even though written this diameter D and this diameter D, little small this diameter on the right hand side, but this diameter are the same. D and D are the same. And he has also asked us to find the diameter small d of this bolt. So what you should see here is when I apply a load like this, this part is under shear, or also this part is under shear, isn't it? Isn't it? If I apply a load, this assume that is a fork, and you have a plate, and you're pulling this part is also under shear. This junction is also under shear. This junction is also under shear, and also this junction which is fitted here, this is also under shear. Okay, when I apply a tensile load, these two junctions are under shear. So what happens is, since if I write, if let us take the above part, this is the above part of the bolt, and you can see here I am applying 80 kilonewton load here. Let us say the load is F. Okay, so half of the load is taken by this bolt, isn't it? F by 2 is only taken by this, and then this is F by 2 like this in this side. Similarly, below also, if this is the bolt, if I apply pull like this, F by 2 in the opposite sense, it is taken totally F by 2, totally total load of F, these two bolts will support. Sorry, F by 2. Give me a moment. This is F by 2, then it can be F by 2. Okay. 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 Give me a moment. I will clarify this thought. This has to be F by 2. F, it can't be F by 2. Okay. Give me a moment. This has to be F by 2. This has to be F by 2. So totally F by 2, Total this total force is F. The total force is F. This side opposes F by 2. This side opposes F by 2. So for understanding what you should assume is half of the load is shared by the upper part of the bolt, and the rest of the is shared by the below part. Okay, this is what the understanding. That generally there is a confusion which I'll clarify you. But what you should understand is, since two areas are formed, two areas are formed in single shear, we wrote that tau is equal to F by A. Whereas in double shear, there are two areas which are going to share, this area and this area. Generally, the author said since tau is equal to F by 2A. That's it. Since two areas are formed, I don't recall this F by 2 concept. I'll let you know in the next class. What Beer Johnson says is the F by 2 is takes, and he will take some force equivalent and do that. I'll let you know in the next class. But generally, what happens is, since two areas are being shared here, this upper part and lower part, since two area, therefore F by 2a, F by 2a. Okay, this is known as double shear. Double shear. Okay. Now let us come back to the concept. Let it be. Okay. If I write therefore double shear is given by F by 2a. Keeping it in mind. He says that the end of one part is forked, in which the eye end of the other is fitted, and both are secured by a pin of diameter d, passing at right angles to the axis of the bar. This is the definition of the problem. A pull of 80 kilonewton is being transmitted from one end to another through a pin. This is a pin or a bolt. The pull of 80 kilonewton has been transmitted to that. The maximum permissible tensile stress in the bar is 100 MPa. Is maximum permissible tensile stress is 100 MPa is given the first data. Okay, and then load P is equal to 80 kilonewton. Okay, and the permissible shear stress in the pin is permissible shear stress. As soon as you give shear stress, you should write tau permissible in the pin is 80 MPa or 80 Newton per mm square. Find the diameter of the bars and the pin. Diameter of the bars and the pin. What is D and what is D? So tell me, one of you tell me which this is sigma tensile. This is sigma tensile. This is tau is shear stress. So in order to find the diameter capital D, which sigma I should use? Which stress I should use? Anybody unmute and tell me, in order to find diameter D, which stress I should find? Which stress I should use?
Sigma tensile.
Sigma tensile, absolutely. For finding the sigma capital D, I should use sigma tensile. Sigma tensile is equal to T by A, which is equal to, I'll write here, 100 is equal to P load has given 80 kilonewton, 80 into 10 power 3, since circular cross section, pi d square by 4. Now tell me what is D. One of you tell me what is D. So applying a tensile load, this tensile load, 10 minutes remaining. Tell me this. What is capital D? Are you calculating?
1 minute advance.
So,
31.92, sir.
okay, that's 32 mm. Shall I write 32 mm?
Yes, sir.
Yes, sir.
32 mm. Now, for calculating this, why I use D this sigma, because this area, this whatever this part is subject to tensile load. Therefore, I use this sigma is equal to P by A. Whereas when you come across the pin is subjected to shear stress. Then I should use tau is equal to, since it is a double shear, tau is equal to F by 2A. Since two areas have been formed, since it is double shear, tau is equal to F by 2A. I know tau is equal to 80 MPa. which is equal to Fe has given 80 into 10 power 3 by 2 into pi d square by 4. Tell me what is d?
Sir, denominator is not clear.
Okay. Tau, which is equal to 80 MPa, 80, which is equal to F is 80 into 10 power 3 by 2 into pi into d square into 4. Therefore, t is equal to
25.23.
yes, 25.23 mm.
Yes, sir.
This can be a 4 or 6 mark problem. If you have some derivation, if you have some space, you will just ask something problems like this. Okay. Another 6 minutes remaining. I will not continue. I think I will take a class if possible on Saturday and Sunday also. I'll complete this part, module 1, half of that. Another Python session, other things. I need 1 more week for that. Another 3-4 classes. One thing, see, still so many under 6 students have not accessed the Google Classroom at all. At least you could have been accessed that, right? We have shared the important information. We'll be sharing important information in it. Why you are not bothered to at least visit that Google Classroom? Why you are creating Google Classroom on Google sites? Huh? Isn't it your responsibility to access that Google Classroom? I don't know. Okay. Please access that Google Classroom. I have given the assignment that to all the examination question paper problems I've taken. I've scanned and I've made that the first question. Please try to attempt it. Okay, I'll stop at this point. We'll be solving these types of problems in the future classes. Another 5 classes I may require to complete only this part, this whatever is Shear Stress part, and then this Python session another 3 classes, 8 classes. It should be more than sufficient for me to complete this first module. Okay, thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you.